Hi everyone, my name is Scott Fleming. I'm an astronomer at the Space Telescope Science Institute located in Baltimore, Maryland, and I'm going to be doing a short demo of the Astronify Sonification software. Here's the original core team of Astronify. I myself am an astronomer and was the principal investigator of the project. At Space Telescope, I work in the Mikulski Archive for Space Telescopes, or MAST, which has 3 petabytes of NASA data from space telescopes going back all the way to the 1970s, all the way through today and in the future. Our current active missions include the Hubble Space Telescope, JWST, and the TESS Exoplanet Hunting Telescope. We're also working, for example, to support the future Nancy Grace Roman Telescope launching later in 2026. In addition to myself, we had Jen Kotler, who is the designer on the project, Claire Brasseur, who was the lead developer, and Kate Meredith, who from Glass Education, who was our education and outreach specialist. So Astronify is a Python package that's designed to represent one-dimensional data as sound for research purposes. And what I mean by one-dimensional data is simply some parameter plotted against some other parameter. So a common example might be the average temperature every day, or the price of the stock market every second. In the case of astronomy, an example might be the brightness of a star measured every minute or two. So the way we choose to sonify the data is to make a tone for each data point in the data set. So on the bottom left here, for example, I have a chart, a grid, that might be plotting the weight of a baby in pounds as a function of its age in months. And so what you would do is you take your graph paper, or you make your plot with your software, and you take each data point, each measurement, and get its X and Y locations, put them as scatter points. You might then draw a trend line or try to fit some sort of line to the data, and that's how you would do it visually. But what Astronify does, it takes each of those data points and it represents them as a tone. Each data point gets a note that has parameters like the duration, or how long the note lasts, the time between each note, or the interval, and also how the data value is mapped into pitch, particular frequency, and that kind of stuff. And these are all customizable, but they do have defaults as well. So this is just showing how each one by one data point would get a sound played. So to sort of orient ourselves with how the software might work, I'm going to be showing a couple of simple examples of sonifications using some shapes before we get into some real data. In this example, we're plotting a series of data points that have the exact same value. So there's no change in the data itself over time. Each of these blue points that are equally spaced will get a note, and the way we've customized this particular one, which is our default, is to make it so that there's no gap in between each data point's sound. In fact, there's a little bit of an overlap. We do that to avoid clicking, which might happen if there is actually a gap between the end of a previous note, data point's note, and the beginning of the next one, because then there's absolutely no data being played and you end up getting this clicking sound. So by having a little bit of an overlap between the notes, we can get a smooth sound that comes out of it. That does mean there might be a little bit of a sort of wobble sound as the end of one note sort of leads to the beginning of the next one. But what you really should be paying attention to is the pitch of each one and noticing that each note itself is identical. So let's go ahead and play the sound right now. So hopefully you can hear that each of those successive sounds is identical because the data itself is identical. Now here's another example of a trend. In this case, now the data is constantly increasing from left to right. So each data point gets successfully larger, and the way we've chosen to sonify this, which is a choice, but it's a common one, is to make it so that increasing values get higher and higher pitches. Let's listen to this one. So you can kind of see that as the data itself gets from lower to smaller values, the pitch is also getting lower to higher pitches, and how it maps and represents the data. Here's another example, this time the top of a triangle. So now we have the data that's sort of steadily increasing, gets to a peak, and then steadily decreases. Let's listen to that. So with these very, very simple examples, you can begin to see how the sound really maps to the shape if you were to look at it visually or maybe touch like a wooden block. Here's a final example, which is the top of a circle, and as we know, the top of a circle is similar to the top of a triangle, but the shape is much more gradual, right? It increases and decreases in a different, non-constant way, unlike the triangle. And so let's listen to that sound, and you can already begin to maybe imagine what this sonification might sound like. So hopefully you could hear that the sound itself, much like the shape, was changing in a more gradual way, representing the shape. Now, these are very simple examples, but it really sort of orients each person who never really experienced sonification before in how this might work. For much, much, much more complicated data, the sort of intuitive nature and the ability of humans to identify even small changes in sound, even for complex data sets, can really augment visual and programmatic analysis of data sets. So let's jump into just two examples with real data. I'm going to be showing what's called a light curve, which is simply a measurement of a star's brightness over time. So visually what we would normally do is make these measurements. We would plot the star's brightness over time. Higher values might be brighter, lower values might be dimmer, measurements of light, and then we would either look at them visually, we might run some analysis software on them to interpret what we're seeing, but it would be your standard visual methods of looking at plots, but instead we're going to turn these into sound. And one very common and popular thing to do with very, very high precision measurements of the star's brightness over time is to see if there's any objects that are orbiting that star that might cross in front of it relative to our line of sight. And much like a person walking in front of a projector, if a planet happens to do that, it will actually block a very small amount, but still detectable amount of light from its parent star. And if we're constantly watching these stars to see if we can find it, it is a very common way to identify and characterize extrasolar planets, planets that are orbiting other stars. And what ends up happening is they make a dip, looks like a U or a V in most cases. So here's a real example. This is using real data, calibrated and processed from the Kepler Space Telescope. And visually, it looks like the letter U. You will see the star is sort of more or less constant with a little bit of noise or intrinsic variability, but then about midway through, there's a characteristic and very noticeable decrease in the brightness while the planet is going across the star, and then and the planet leaves as it continues its orbit around the star, and the star brightness goes back to its original value. So let's listen to this. I'll give you an example of some of the characteristics that you can use the sonification data to better understand. It would be the details of the dip itself. So lots of the very detailed parts of the shape of this signal, everything from the symmetry to the depth to the duration to what's happening during the actual maximum decrease in brightness, all give us information about how to analyze and interpret the data, particularly the properties of the planet itself and the properties of the star. And so combining this sonification with other methods of measuring parameters and comparing them, we can really get a maximum insight into what's happening. Finally, I want to show a slightly more zoomed out view. So in this case, we're plotting the brightness of a star over time. And it's really important when we're looking for these very small dips in brightness to be able to repeatedly see them, because as the planet orbits around the star, if we wait until it goes all the way around again, we should see it transit, multiple times. And that really can help us differentiate possible false positives because of other reasons that the star may have dropped in brightness. Maybe there's some other effects happening on the star, maybe it's an error in our calibration, but if the planet goes in front multiple times and we see a consistent and repeated signal, we know it's real. So this is, again, real data from the Kepler telescope, and in this case we have a planet about the size of Jupiter orbiting around its star much, much closer than Mercury orbits our sun, and it actually makes 3 complete revolutions around the star in about 9 days. So see if you can listen and hear the 3 dips as it crosses its parent star. So in addition to the dips, if you listen really carefully, you might have also noticed that slowly the overall sound was getting a little bit lower as well. And so in addition to hearing and recognizing when there might be sudden and relatively short drops in brightness, we can also pick up additional details like what might be happening to the star itself over much longer timelines as well. So thanks a lot for listening to this demo. Again, my name is Scott Fleming, and if you want to learn more about Astronify, you can Google search or visit our homepage, astronify.readthedocs.io, for all the information you want about our open source package, tutorials, and even some fun interactive surveys you can take to help us test our sonifications. Thanks again for your attention.